Welcome everyone to the ISPASS tutorial on Esp. Esp is an open source platform for Agile system-on-chip development. Esp has been open source for the last 18 months or so, but it is actually the result of over 8 years of research at Columbia University by the system level design group that I'm leading. And together with me, I have 3 members of the group who are among the main developers of Esp to introduce the various capabilities of this platform to you. So the agenda for the day, the tutorial is structured along essentially 8 parts. We will have an overview presentation and a very brief concluding part on some of the resources available if you're interested in organizing courses around Esp or teaching with Esp, the topic of system-on-chip architecture and programming. The main core of the tutorial are these 6 parts that you see here, where you have the opportunity to learn about how you can use Esp to design and integrate accelerators, specified in various languages. As you will see, Esp has a methodology that embraces a variety of languages and tools into design flows. So the 2 of the main segments, actually 3 of the main segments, are about the design of the accelerators using System C and high-level synthesis, using C++ and high-level synthesis. And for a particular application domain of embedded machine learning, there is a design flow that allows you to design accelerators starting from common framework for specifying particularly neural networks like Keras, PyTorch, or ONNX. 2 other important parts of the tutorial are about the integrations of accelerators inside and system-on-chip architecture organized according to the Esp architecture, and we will tell you more about that in a second, and as well as integrating accelerators that are already pre-designed and developed and are available as open source hardware from third parties. And there is, of course, one very important aspect, which is how you bring everything together. So how you use Esp to realize the prototype of a system on chip, which is multi-core, it has multiple processing cores, and a variety of different accelerators, possibly designed with different design flows and languages. So this is the agenda, and as we have already said, that there will be the opportunity for you at some point soon to follow some of the tutorials by practicing a few of the steps for these segments. So today with me, my name is Luca Carloni. I'm a professor of computer science at Columbia University, and where I lead the system level design group, and I've been working on various aspects of embedded system design, design automation, and system on chip of design for almost 20 years. And the rest of the team today consists of Paolo Mantovani, who is an associate research scientist at Columbia University and is the main architect of Esp. Giuseppe Di Guglielmo, who is also an associate research scientist at Columbia University, and he contributed to Esp along various paths, among them the design of accelerators and the design flow to optimize and synthesize accelerator with high-level synthesis tools. Today, we will focus particularly on the presentation on designing accelerator with starting from C++ and using high-level synthesis. And Davide Giri is a PhD student in the system level design group at Columbia. And Davide contributed also to many parts of Esp, particularly to the whole architecture of the memory of a system on chip, including supports of various modes for cache coherency, as well as to the design flows of accelerators, and to a lot of the infrastructure that supports the sharing of our contribution in open source, and including, for instance, all the infrastructure to support a tutorial like the one that you are assisting today. So why did we develop ESP? So this goes back actually to several years ago, to the motivation of quite a bit of the research that the system level design group at Columbia has been doing. We believe that information technology will increasingly rely on computing systems that are heterogeneous, more and more heterogeneous. With heterogeneous, we mean that these systems consist of components that have different nature, particularly components that execute software, so processor cores, general purpose processor cores, to a certain extent, application-specific processor cores, as well as, together with peripheral and memories, a variety of specialized hardware blocks. These we refer to as accelerators, like many people do. And in this picture here, you see, for example, an ESP system, which consists of 12 components, and there are 4 processor cores, 2 I/O peripherals, and in this particular case, 6 different accelerators. So these accelerators are out of core, meaning they are designed independently from the processor. They are specialized for a special function, and for this function, they provide high performance and energy efficient implementation compared to an execution in software. So, sorry. So the fact that systems increasingly are becoming more heterogeneous is something that you can observe across a variety of products in the information technology industry, from embedded system all the way to data centers. And you have the more and more, it is more and more the case that application runs on heterogeneous architecture. This brings a lot of advantages in terms of performance and energy efficiency, but also challenges, because you have systems that are less homogeneous and therefore less regular, and this has impact on a design time, a runtime. It changes many aspects of the hardware-software interface. It requires to handle in an efficient way the management of shared resources across components that can access them for different purposes. This brings this issue of design complexity, and an important way to handle design complexity is to use better levels of abstractions and to promote design reuse. And so we think that in order to do that, so design reuse both within an organization, across organizations, is important to have a new approach in the development of computing platforms, where we define a platform like the combination of a computing architecture and design methodology that rely on design flows with the support of electronic design automation tools. So this is the overall view, and in this context, to support the reuse of components and to simplify the integration of components developed by different organizations in order to develop a new heterogeneous computing engine like a system on chip, of course, is very important the role that is assuming open source hardware. Open source hardware really, in our opinion, is also an opportunity to re-energize the innovation and the research in the semiconductor and electronic design automation industry. So probably you are aware that the open source hardware community has been gaining momentum over the last few years, with many diverse contributions from academia, from industry. There are multi-institutional organizations that try to coordinate the various efforts. Some of these contributions and efforts are highlighted here in this slide, and you have some of the links, and there is quite a bit of support also from government. So open source hardware is really a great opportunity, and ESP really is an effort in the context of open source hardware. In this context, we think that ESP brings a somewhat unique perspective. So ESP is a platform, and as we define it, a platform is a combination of an architecture, a computer architecture, and a design methodology. The architecture and the methodology are developed together, and this is key in order to have innovation, because really the assumption that we make on the architecture helps to develop more effective methodologies, and the methodology in turn simplify the use of the architecture to accommodate the reuse of components developed independently, simplify their integration and their programming. What you see here is the website of ESP. As I said, ESP has become an open source project about 18 months ago. So we have, during this period, we have gone already through a few releases. The website here is a snapshot taken earlier this week. So you see that there are pointers to the release and actually to today's tutorial. And in the website, you really have the opportunity to access a variety of resources that we have made available and we continue to make available because ESP is an ongoing project. So you have access to the GitHub repository with all the code that we have shared. You have access to quite a bit of resources for learning about ESP. There are hands-on tutorial, shorter like of today's tutorial, focusing on particular capabilities of either the architecture or the methodology. You have access to the links to the YouTube channel where we put videos of tutorials and presentation given at conferences. And you have the opportunity to participate and contribute, not just as a user, but potentially also as a collaborator and a developer as we do with open source projects. Maybe here, I don't know, Davide, should we stop 1 second and you want to again go very quickly?
No, I think it's okay. Then Paolo will just recap a couple of concepts about the Docker when it's
very good. So let me conclude this introductory part by saying a few key concepts with respect to the concept of platform and how this is really realized in the context of ESP. So I said this already 2 times. One more time. For us, a platform is the combination of an architecture, computer architecture, and a methodology, an electronic design automation methodology. As you will see throughout the tutorial, and I hope we will really appreciate, a key attribute of the ESP platform is flexibility. The architecture is built based on certain assumptions, but we believe is fairly flexible and accommodates a variety of approaches in combining heterogeneous components like processor accelerators and interconnecting them. The methodology builds on top of the assumption of the architecture, but is very flexible in the sense that it accommodates a growing number of design flows to develop, optimize, and integrate these components. Why I'm stressing this concept? Because the architecture is important in order to enable the design reuse of components, and this is key to address the complexity of designing and programming system on chip and in general heterogeneous computing engines. And so an SoC architecture, in order to enable design reuse, must automate the integration of the components that are independently developed. Dually, an SoC methodology should enable design collaboration, collaborative engineering, if you will, and can do this when it allows designer to choose the appropriate specification language, level of abstraction, and tool flow for each different component, each different intellectual property block, if you will. Some components are better designed with certain languages and certain tools and certain design flows, while others benefit from a different approach. And we want to be flexible with respect to that. So it is the effective combination of the architecture and the methodology that together provides this agile design flow, which really we believe can enhance the potential of the open source hardware, which is something that, as we said, could be strategic with respect to really give a great impulse to research and innovation in the age of heterogeneous computing. So a few words of introductory on the Esp architecture and on the methodology, and then I will, Paolo will continue and go into more details. So the architecture, here you see a sketch of an instance, very high level sketch of an instance of a possible ESP architecture for a system on chip. This is a simple one. You see this matrix of tiles, 3 by 3 matrix with 9 tiles. And really, ESP has this tile-based approach. Tiles are heterogeneous, but there is a certain level of regularity, at least from a conceptual viewpoint, things may be different when we go to a physical implementation of a design, but a certain regularity on how these tiles are organized. So there are, first of all, certain classes of tiles, main classes of tiles. So some, for instance, here the red tiles are processor tiles, the green tiles are accelerator tiles, the blue ones are memory tiles, and the orange one is auxiliary tile. And then more recently, we have developed a new type of tile, which is the shared local memory tile, which we'll tell you more about later. So this tells you two things. First of all, the type of tile is not a fixed structure. The concept of tile is, and tile can be combined to really obtain a variety of different instances of ESP systems. In this case, you have a 3x3 tile matrix. Of course, the number and mix of tiles may change. And so this is a compromise between supporting heterogeneity of component and specialization, which is more specialization both in the context of the characteristic of the tile matrix and the specific of each tile, the content of each tile, and at the same time have a certain degree of regularity, because tiles are connected through interconnect, which is typically a network on chip, scalable network on chip, highly configurable, as you will see later. And tiles get connected to network on chip through an interface, which is referred to as a socket. So each tile has its own socket. In fact, an instance of a general concept of socket, since sockets are a little different for each main type of tile. There are sockets for processors, sockets for accelerators, and so forth. And sockets don't just provide an interface to the network on chip, but they also, and this is very important, provide a variety of so-called platform services. So for instance, among the platform services is how you configure accelerators, how you access the memory hierarchy, how you manage coherence, how you manage interrupt request, and so forth and so on, how you manage, for certain systems, the dynamic scaling of frequency and voltage. So these are all capabilities that we have designed, tested, and developed across many systems, and that we make available to the developers of SoC, processor, accelerator, who can rely on these existing platform services. A lot of these services are highly configurable at design time. To a large extent, some of them are also configurable, reconfigurable at runtime. So if this is the high view of the architecture, let me also give you a high view of the methodology. As I said, like the architecture, the methodology has the goal to provide a nice compromise between modularity and flexibility. So the methodology really embraces a variety of different design flows. This particular picture shows different design flows to develop components that end up into the so-called ESP library of components. Some of these components are hardware components, some are software components, and often, like in the case of accelerators, when you develop a component in hardware, you also develop the support for the integration from a software viewpoint. Now, let's take the case of accelerators, for instance. We know that accelerators are specialized hardware blocks, and so an accelerator in ESP can be designed with different design flows. Starting from the bottom in terms of level of abstraction, designer can develop an accelerator using design flows at the register transfer level, or RTL, using such languages as Verilog, DHDL, System Verilog, or Chisel, and essentially logic synthesis. Raising the level of abstraction, we, as an ESP team, often promote the design of accelerator using higher level programming languages like System C or C++, and we support the integration within the ESP methodology of tools and flows, commercial tools and flows like Vivado HLS, Stratus HLS, Catapult HLS, which are all different offering to use high-level synthesis, HLS, to derive from this high-level specification in C++ System C, optimized implementation in terms of synthesizable RTL, often synthesizable Verilog. But we can go beyond that. Depending on the particular application domains, the ESP will continue to accommodate the development of new design flows, which are application specific and provide certain advantages. Concretely, today, one of these flows is for the machine learning, in particular neural networks, with an emphasis on embedded neural networks. And here, ESP leverages another open source project to which we contribute. A large open source project is called Hpls for ML. And among other things, Hpls for ML provides a compiler to go from common frameworks to specify accelerators for a neural network application. Such frameworks are like Keras, TensorFlow, PyTorch, or ONNX. Hpls for ML takes a specification of a neural network in these frameworks and produces synthesizable high-level specification for the accelerators. So produces, for instance, synthesizable C that then can be used in high-level synthesis, can be used to obtain a hardware implementation in synthesizable RTL, and that implementation can then be integrated, thanks to the ESP flow that we developed, in a complete system-on-chip system together with a variety of other accelerator and processors. So this integration happens through the SoC flow, which is what we show here in the right part of the slide. Once you have developed components with different languages and different tools and into the ESP libraries, then we have a support, largely automated support, guided with a graphical user interface that I will show you in a minute, to combine these components into the instance that you desire of the particular SoC. So for instance, you define a certain matrix in terms of number of tiles, and you can choose how to populate, if you will, the tiles with different components. And then through a largely push-button automated flow, you can obtain rapidly a prototype that you can run on an Fpga, and through other tools that ESP provides, obtain a software build such that on the Fpga, then you can boot a full-fledged operating system like Linux and test, evaluate your design, the design of your SoC, the design of maybe an additional accelerator you have developed and combined with existing processor and accelerators running real applications. And this is something that we have tested over the years and we continue to augment in terms of capabilities. So just to give you a very quick view of something that is possible and that you learn through this tutorial today, this is a snapshot of the ESP GUI, ESP graphical user interface. As you can see, the user in this case is developing an SoC with is a simple one to fit into the slide with 3x2 tile matrix, 6 tiles, combining processor, I/O, specialized accelerators, third-party accelerator, deciding different type of processor. As you will see later, there is a choice on the processor core and the supporting different instruction set architectures. And you know the cache configuration. You can configure the network on chip, which is often very critical for the performance of your system. And also there are quite a bit of capability to evaluate the system, to monitor the execution of complete application in a system like this, and therefore refine potentially the design of component or the configuration of the network on chip or other aspect of the system. And this will be hopefully one important takeaway for this tutorial today, is how to use ESP to do your own research to develop new accelerators or new components of the SoC and being able to evaluate them in a complete system, as this slide shows. So here at this point, I stop. If there are questions before we go into the details of ESP, and I'll let Paolo go into that section. But let's first, 1 second, stop and see if there are any questions. Since it can be question in the chat, or maybe just unmute yourself and ask question directly.
I can switch the monitor in the meantime if you stop sharing.
Yeah, sure. I stopped sharing, so you can switch.
Hello, can you hear me?
Sure.
I have just a little question.
Please.
In your framework, do you allow, for example, big little architecture? Like I know Big Little is especially is for ARM architecture, but do you allow, for example, I think you use RISC processors? Is that correct?
Yeah, as Paolo will show in a second, we support RISC-V, some open source process, the integration of open source processor core implementing the RISC-V instruction set architecture, particularly the Ariane core and the Ibex core. And we also support a different instruction set architecture, which is Spark, through the integration of the open source Leon 3 core. I'll let Paolo further elaborate on to which extent we support a Big Little architecture. Big Little, as I understand it, is the combination in a multi-core architecture of cores that have different capabilities. Like, for instance, a high-performance core, potentially implementing a 64-bit version of an instruction set architecture, together with a smaller low-power core that maybe implements a 32-bit, as an example. So ESP allows you to combine different processors. Paolo, I don't know if you want to just you were going to say on how this combination currently is possible and what is planned for the future.
Yeah, so at the moment, the Big Little scenario is not available simply because there are no two cores, one big, one little, that actually run the same ISA, right? So if you were to instantiate two different cores, one would have to be the one running Linux, and then you would have that core to kind of use the other one as an accelerator, for example. If you really want to support that sort of architecture, I think we would need to integrate two different cores with two different capabilities that do support the same ISA. And then at that point, I don't see any issue against that, honestly, in the platform. The architecture is very flexible, so that can be accommodated, but it's not available at the moment, mainly because of the type of cores we're supporting. Does that make sense?
Yes, yes, thank you very much.
All right, so before we move into the hands-on part of the tutorial, I just want to briefly show a little details about each tile so that you have an idea of what is available into these sockets that Luca was mentioning, so that you can understand how each component is actually integrated. And this is going to be really a brief and quick I think it has timing for some reason. Sorry, let me remove that. Presentation of the tiles, but just really to give you an idea of what's inside. So we do have processor cores in our architecture, of course, because you do need to run software, but really the platform gives you equal weight to all components in the architecture. And accelerators are, in our opinion here, key to make the system heterogeneous and really domain specific, right? So these components, the accelerators, are what make each instance of ESP unique with respect to the general architecture, which per se is a general purpose platform. So in the accelerator socket, you find all the components that we don't want the accelerator designer to be rethinking over and over again. So you'll find an optional private cache to have full coherent access to memory. You'll find the DMA controller. You'll find a dedicated TLB, which is specialized for accelerators in this case, to handle virtual memory. And here, by virtual memory, I really mean when you're thinking about your algorithm that you want to accelerate, and you're thinking about your, for example, C implementation or anyway procedural implementation of your algorithm, you have data structures like arrays. And we want the designer to still think about that as in terms of arrays, like when you do using high-level synthesis. And then based on that information, offset within an array and length of a transaction, then we translate that into an actual memory access, which can be coherent, non-coherent, or as we'll see later, it could have different flavors of coherency. Now, the TLB here is the key to support that translation without the user having to think about that. And then, of course, as Luca was mentioning, some control for dynamic voltage frequency scaling. We have support for accelerator to accelerator communication, interrupt deliver, and so on. And so what you have to do here is just really thinking about your accelerator. And this is what we're going to do in the first hands-on tutorial. When you design these sorts of accelerators, typically you leverage a lot of parallelism in your data path. And one thing that you need if you want to support this parallel data path is to have private local memories, or you can call them scratchpad, although in this case, we consider these memories to be just dedicated to the accelerator, so they're not really exposed to the processor. But you still need these SRAMs, these on-chip memories, to support the parallelism of the data path. So you'll be loading some data into this memory. The accelerator would be running out of the data that are in the memory, compute some temporary results, and then store them back to the main system memory hierarchy. And in order to support parallelism here, you need these memories to be typically multi-bank, shaped in a way that are really targeted to your target application. And so we do support the automatic generation of these memories based on a few simple user inputs. The different flavor of accelerator tile that supports the integration of existing IPs. So when you are in a scenario where you already have your RTL for your accelerator is the third-party accelerator tile. And in this case, most of the services that we have in ESP are kind of assumed to be inside of the third-party block. So if you take most IPs that come with some standard bus interfaces like AXI or HP, they would already issue actual memory requests on this bus. So all of the virtual memory and DMA transaction are kind of handled by the combination of the third-party software and the third-party accelerator interface itself. So what we provide here is a series of bus adapters that translate all of the memory transactions to the network on chip protocol, which can also be coherent or non-coherent depending on what you select, as well as the interrupt delivery. And the most important part about this style is that it's built in such a way that you can control your accelerator with the unmodified third-party software. This is very important. You don't want to have additional time needed for the integration in rewriting your software. Now, in the processor tile, we still have some of the services that you would find in the accelerator, like, for example...
Paolo,
yes.
While you explain this slide, maybe I already addressed it by writing, but you can address the question in the chat about integrating ARM cores. Oh,
sorry, I didn't see the chat right now.
I already replied. You can see my reply, but maybe you can add some.
Yeah, so thank you, Davide. So in the processor tile, as I was saying, we still have, for example, the private cache to support fully coherent memory accesses, and we also have the bus adapters to support the integration of the processor cores. In addition to that, in this tile, we have some adapters to the interrupt protocols, which are typically specific, not just to the ISA, but to the processor themselves. So right now, we have 3 different adapters for Ariane, IBEX, and Leon 3. And to address the question, ARM processor cores, definitely we can integrate them too. At the time we started the project, there was no processor open that could actually boot an operating system. And that's the main reason why you don't find at this time the integration of an ARM processor core. Definitely that can be done. And it's just a matter of really spending a little bit of time to design these adapters specific to the interrupt protocols mainly, and making sure that we also have adapters in case the processor relies on a specific coherence protocol, because typically what we take is not just the processor core, but also the level 1 cache, which is tightly coupled to the processor and is part of the overall microarchitecture. And if the level 1 cache expects some specific protocols for coherency, then we need to have a little translation unit on the bus such that we can interact with our own protocol on the network on chip. All right, and of course, all the processors capable of booting Linux boot the unmodified version of Linux. We do not want to have any ESP-specific patches in Linux to be able to boot. Now, in the memory tile, you don't find the socket because we don't assume people will actually integrate components and IP blocks in the memory tiles. This is more of a service given to processors and accelerators. And so what you find here is all the components that support the different level of coherency. So we've got a partition of the last level cache, if available in the target technology that you're, for example, for ASIC, if you have it, or FPGA, there's an adapter to a DDR controller on a bus. And if not available, we also support a custom FPGA link, which allows you to use the FPGA as a proxy to access memory. Also, we have a sequence of proxy components that allows you to select different models of coherency for your processing engines. So when memory requests get to the memory tile, they can be served either directly by memory or by the last level cache. And when they're served by the last level cache, they can be served in a last level cache coherent mode, in which we do not involve any private cache in the communication, or using the full coherency protocol, and therefore being able to actually exchange data that might be owned by a processor or another accelerator in their own private cache. And this is all implemented within each of the memory tiles. And you can instantiate multiple of them, of course, depending on the bandwidth that you need for your specific target SoC. Now, the latest addition is a scratchpad tile. And in this case, the scratchpad is really a scratchpad, which is software managed, and you can have both CPUs and accelerators address in this make address request to this scratchpad. And this tile really has the memory itself and a lot of components to translate all the type of the requests that the processing engine can make into a scratchpad access. So we support CPU and accelerator DMA, memory mapped IO access, and in the future we plan to support also fully coherent access in the scratchpad and reconfigure it at runtime. But for now, the coherency planes are used for a small cores like the IBEX when you do not instantiate the memory hierarchy to make regular read and write requests to the scratchpad. Okay, on top of this architecture, we have a super simple API that is part of the skeleton test application for the accelerators that we generate whenever you design a new accelerator. And the API is meant to help designers quickly move from the design of the accelerator to the full system execution with full software stack. So this API runs on top of Linux, and it allows you to do two main things. One is allocating memory in such a way that it is efficient to access from both the processor core and the accelerators. And of course, avoid any sort of data copying from the processor memory space to the accelerator memory space. And the key idea here is to use large pages, and depending on the target system and target ISA and architecture of Linux, for example, there are different primitives that we can use to implement that. Now, the second thing that the API does for you is being able to invoke the accelerators, not just one, but even more than one in parallel, by using a simple configuration structure that will enable it once all the accelerators configure them, eventually even for point-to-point communication when necessary, and allow you to run them in parallel. So this is very helpful when you're trying to create a pipeline of accelerators, or for example, see the effects of having multiple components executing at the same time in your system. And of course, these run on top of a kernel mode driver that is completely generated for you, and then on top of Linux. All right, so here I want to move to the first hands-on tutorial, and which is about designing an accelerator in System C using the automation flows in Esp. Most of this part of this tutorial can be done using the Docker. So please, if you had trouble booting the Docker, please let us know now. We can briefly help you there. And you can find the information. You should still be able to see my screen when I swap. So on this page, you see that under the program, you'll find the hands-on steps of the tutorial. So if you click on the instructions, you will see all the details and the information about what I'm about to do. Do you have any questions here? Okay. So this is what we're going to do. When we run the automation script in Esp to generate the skeleton of an accelerator for the System C flow or the C++ flow, what we're really doing is creating several files that get integrated into the Esp folder structures. So the most important part is, of course, the design of the accelerator. There is a structure that we follow when we design this type of accelerator, which is split them into at least 4 concurrent processes. One handles configuration, and it's basically the interface with software. So software will interact with this portion of the accelerator to configure user-specific registers, like, for example, if you're doing an FFT, the length of your vector. And then there are 3 main concurrent processes which execute for the entire period of time in which the accelerator is enabled, which load data into the local memory, this private local memory that is also generated automatically, compute based on your input, and this is really where the designer focus to create a specialized IP, and then write the results into an output local memory and then store them back. Now, these three processes, what we aim at is to make them run in a pipeline, and as much as possible, and this is oftentimes achieved by configure HLS configuration settings to achieve an almost perfect overlapping of load, store, and compute. This way, you can hide the latency of bringing your data in and storing your data out of your accelerator while computing. So let me switch to the shell. I see some questions. Okay, no, all right.
It was just about the link. Yeah, I sent it. Let us know if you have problems with the link.
Okay, so if you are on your Docker now, you should have your ESP folder. Please enter that folder. And the first thing we're going to do is to run the accelerator generator script, which is located in tools, actgen, actgen.sh. So we just run this script. And for this tutorial, we're going to use really a toy example so that you can really focus on the step and not too much on the implementation itself, but you can complicate the computation phase as much as you want in general. So we're going to call this sub. We're going to select the default Stratus HLS flow. If you are in the ESP folder, this will be actually the right folder to start. So this is just like the root for ESP. So just press enter. We're going to pick an ID. Now, for example, let me use 061. And here is the most important part of this script. Here we're asking users to list configuration registers. So here we're going to do like a very simple subtraction element wise. So I'm going to define a register that is called subblend. And the script is going to ask you what's the default value for this register. The reason it does so is because we're also generating a sample test application. And so with this parameter, we're going to create your initial test application. So let me select, for example, 8. And then the maximum value, which is also important, is going to be used to size your private local memory. So let's say that at most we are sending vectors of 1024 elements. Now I'm going to create a second register, which I call sub batch. And what I plan to do with the second register is allow my accelerator to run this operation on multiple vectors without software interacting. So we don't need to wait the CPU every time we send another vector. Now in this case, let me use just, for example, 2 as a default. And for example, 400, I think this is the this is what we wrote in the instructions as a maximum value. So at most, we're going to batch 400 vectors. All right. When you're done listing your registers, you just enter nothing in the name, and the script will move on to the next stage. So here we're asking what is the default token at each transaction on the bus. So for example, we can use shorts, and then you would select 16 bits. Now, you may have scenarios in which you need to load different type of data types. And in that case, you would need to specialize the load and store functions to do that. That is absolutely supported. The script, though, asks you for like the main type of data token. And now here, when it says enter the input data size, what we want is for you to think about a function of the configuration registers that defines the minimum size of input on which your accelerator is able to compute. So if we want this accelerator, for example, to apply an element-wise operation on a full vector, we need that at least our memory can hold the entire vector. So the input data size for us is going to be the length, the register. And again, think that this is a user configured register, so you can change this value at runtime. All right. So the input maximum data size is basically 1024 tokens. Now, in this case, since it's element-wise and we're going to return the same vector, also the output is going to have the same size, subblend. Okay, so assume that this minimum size is really large and you're only willing to allocate a certain amount of area on your chip or a certain amount of resources on your FPGA for your accelerator. So what this chunking factors allows you to do is to create a smaller local memory and generate the logic necessary to load a portion of the input, let you compute on that, store back that portion, and then read the next portion. So, for example, if you choose 2 here, you would have your local memory that can hold just half of the size of your vector in this case. Now, to keep it simple in the tutorial, we're just selecting 1, meaning that the memory will be able to hold the entire vector. So at every load transaction, you'll be reading a full sub-length a number of elements. And you see that the script computes for you the size of the input and the output buffer. Now, how many batches do we want to run? Well, this is precisely the reason I created the second register. So I'm going to use the second register as the function here. So batching factor maximum is going to be 400. Now the script realizes one thing: input and output tokens are exactly the same. So do we want to store the data in memory in place to save memory footprint? Let's say yes. So in this case, the output buffer in main memory this time is going to be overwritten as we compute. Okay, so this completes the generation of the script. And if you move to accelerators, Stratus HLS, substratus, this is where the accelerator skeleton has been generated. Everything clear so far? Please, if you have questions, I'm going to stop for a second before moving to the next phase. All right. Please stop me anytime if something is not clear. So we move to the hardware. All right. Shouldn't have done that, sorry. We move to the hardware folder, and you see that there's an HLS folder. This contains the script for high-level synthesis. You can quickly check that. We don't need to change this script if you want to just run a basic example. But of course, you're free to add here any sort of pragmas and directives for synthesis. One thing that I want you to notice is that we already defined at least 2 configurations for HLS, which depend on the size of the DMA. You see 32 and 64 bits. And this is because we can instantiate an accelerator in an ESP system based on a 32-bit architecture, like for example, IBEX and Leon 3, or 64-bit architecture using Ariane. So we already have predefined these 2 HLS configurations for you, and you can clearly add more. If you move to the source folder now, I want you to open sub.cpp and look for compute phase. Yeah, computing phase implementation. So here we're going to do something very simple. Instead of an identity function, which is what the skeleton creates for you, we're just going to subtract something to each element, right? And notice that we're doing this for both ping and pong buffer. The script already for you generated this ping pong buffer implementation such that you can really pipeline, load, compute, and store. At every iteration, you will be loading one buffer, computing out of that buffer while we load to the next one. And similarly, storing data from one buffer to memory while you compute the new set of data into the other buffer. So this ping pong implementation has already been done for you. Okay. So this is really the place from compute on where you want to implement your own algorithm. Okay, and in this case, we're keeping it simple, but you can really write any type of C++ code that the high-level synthesis tool can digest. All right, now you move to the test bench folder. And what we need to do, since we've changed the behavior, it's not an identity function, is to open the system.cpp file, which is really the test bench. And you can look for input, data, and golden output assignment. So the test bench is being pre-built for you as well, but we need to change the way in which we assign our golden output. So we apply the same type of operation here so that the golden output will be computed based on what's your target application. And obviously, this can be complicated at will. And even the input can be randomized, can be taken from a file, anything that is specific to your target application. All right, so with this, we already have an accelerator that can be synthesized, and a working test bench. So from the SoC folder, and for this tutorial, we're using the VCU 118 design template folder. So you can just enter ESP, SoCs, Xilinx VCU 118 folder. Make sure you have your environment set up. I'm just going to check I do have mine. Yeah, so the environment for the tools is set up. Now for this step that I'm running here, you need to have a Stratus library, so you won't be able to run this, this simulation. But basically what you can do now that the accelerator is there is substratus execution. So this is going to compile, and this is plain system C behavioral execution. Your accelerator code, it's going to compile the test bench and run it. And then it's going to print validation pass or not. Of course, you can try using a different element-wise operation and you would see a failure here. Now let me also run, because this takes a little time, Stratus HLS. And before I do that, I'm going to do something to make this faster. So I pre-built the cache library for this accelerator, because this step can at times take a little while. So you see that in this HLS work folder, which would be built for you, basically, we have a cache lib pre-built. And this should be, sorry, inside the hardware folder here. All right, so now that I have copied the library, let me just run HLS for you, which is going to be run like this, substratus HLS. Let's see. All right, so the first step that you're seeing here is our memory generator script that is creating the memory subsystem for you. So as part of the generation of the accelerator skeleton, we've also generated a list of input and output buffer for now, and you can improve this list if you need more local memory buffers. And from this list, Esp is generating for you actual memory banks based on the target technology. Now, in this case, the technology is Xilinx Fpga, so we're using block RAMs. And it shows you a quick log of how these memories are being created. And then high-level synthesis is going to run on both HLS configurations. While high-level synthesis runs, and we let it run for a few minutes, now that I've copied the library, it should be quick. We move to the software folder, and you see that here we have generated a bare metal application as well as a few Linux components. There's a driver, this is a kernel mode driver, an include header file, and then an application, which is the skeleton for a test application. So let me start from the bare metal first. We're going to edit the sub.c file, look for the init buffer function, and you see that here we are initializing the input, same as we were doing in the test bench, and our golden output. So we apply to the golden output the same element-wise operation. Then we go back to the application in Linux, look again for init buffer, same type of function. This is a Linux C application though, and we apply the same element-wise operation. Okay. Okay, so HLS is completed, and as part of this operation, HLS has created a couple of folders. You should see in the instructions. Let me share for a second the browser here. These folders have been created together with the generated from HLS Verilog of the 2 HLS configuration of the sub accelerator. And if you want to continue with the next steps, please create manually these folders because you're not able to run HLS without a valid license of Stratus. So of course, when you run HLS, this will be created automatically. But in this case, we need to manually create the folders. By creating the folders and copying this XML, you allow the ESP SoC flow to see the accelerator and instantiate it in the next phase.
So here you also see FFT, which is another accelerator that we're going to use in the next steps of the tutorial. It's one of the accelerators already available in Esp. So basically, you guys are not running HLS. We just create the folders as if you did.
Exactly. All right. So last step before I pass the ball to Davide, who's going to present the SoC flow and more accelerator design flows. Let me just run the substratus simulation. So when you run this target, this is really running the unit test bench that we just edited against all of the views of our accelerator. So it's going to run the simulation against the behavioral version, so system C. It's going to run it against the generated RTL for 64 bits and the generated RTL for 32-bit DMA. So compiling within the environmental stratus is a little slower, but this is just going to happen the first time. And it's just going to run a co-simulation of system C and RTL. And this is very helpful because you can very quickly make sure that your synthesis pragmas and your memory subsystem implementation that has been generated based on your list are correct. In fact, when you have a mismatch between behavioral simulation and RTL simulation, the reasons are typically because of memory or high-level synthesis pragmas that do not reflect what your code is actually doing, right? So you need to make sure, for example, that you do not break dependencies that are in your C code. So this is the behavioral system C. Next is going to run system C RTL, 32-bit DMA, and finally 64-bit DMA. And you see that it's the same test bench that runs against all views of the accelerator. All right. So this concludes my part. Next step, I think, is compiling software, right, Davide? I'm going to stop sharing.
Yeah,
if you have questions, please post them. I can reply in the chat or over Zoom. Okay.
Okay, thanks, Paolo. I'll start sharing, and if there are questions in the meantime, please go ahead. You see my browser, right? Okay, so yeah, as Paolo said, just make sure to do this step. You can just copy and paste so that the ESP GUI will see these accelerators as if you ran high-level synthesis. Okay, so this is where we are. Now, if you notice, one of the things that you guys generated and then slightly edited with Paolo are the bare metal application, the device driver, and the Linux application. So what we're gonna do now is to compile those. So I'll move to the terminal as well. So as you may have noticed already, the place where you launch all the make commands in ESP is from these SoCs folders. In this case, the SoC design folder for the VCU 118 Fpga. So simply to compile the bare metal application of your accelerator, you just need to do make name of the accelerator dash bare metal. Oh, and by the way, just to remind everyone, if you are in the Docker, before you launch these make commands, remember to source, like I did here, to source these. Otherwise, when you launch make targets, it will complain. Okay, so this is to compile the bare metal application for the sub accelerator that you guys created. Then we're also going to compile the application for one of the accelerators available in ESP. It's called FFT. It's for fast Fourier transform. Now, when you compile this application, where do the executables go? They're going to be inside this local generated folder called soft build. Then in this case, I will show you in a second that we're compiling for the Ariane processor core, so Ariane folder, and then bare metal. So if you see in here, we have the executables for the bare metal apps that I just compiled. I'm saying that we're compiling for Ariane because we have not modified the default configuration for the VCU 118. And the default configurations, which are in the dev config folder, if you see, for example, for the VCU 118, this is a default ESP configuration. As you can see, the default CPU architecture is Ariane. Later, we will see how you can use a graphical interface to change this configuration. Okay, so we compiled the bare metal app. Then the other things that you guys generated is device drivers and Linux applications. Now, in ESP, simply by doing make Linux, then to go a bit faster, we can do -J4. You not only compile Linux and generate a Linux image for the Ariane core, but you're also automatically compiling all the accelerator applications and all the accelerator device drivers. It's implicitly done by this command. Now, if you launch this now, it will take a while. In the meantime, I will show you other stuff. In my case, I pre-compiled it, so it's going to be faster. If you want to just compile the accelerator test applications or device drivers without compiling the whole Linux, maybe when you're testing, experimenting, what you do is similar to what we did for the bare metal. You can compile just the Linux application. Now, nothing to be done because I already compiled it with the make Linux, or just the device driver. Okay. Again, where does the compiled software go? In soft build, Ariane, in this case. And here you can see that now you have a root file system. You have a Linux build. And more importantly, the linux.bin is the actual Linux image that we will use when we go and test our system on Fpga. Okay, so maybe your make Linux is still running, it's possible. I'm going to show you something in the meantime. So now we have the software ready. We take a step back and we prepare an additional accelerator before moving into the actual SoC design. And the additional accelerator that we're going to prepare is NVDLA, is the NVIDIA Deep Learning Accelerator. And it's the accelerator that we use to create and demonstrate our flow for integrating third-party accelerators. The idea is that what you've seen with Paolo and what you will see with other presentations later is that with ESP, it's easy to create new accelerators with different tools and flows. With this third-party integration flow, we want to also make easy for you, or at least easier, to integrate pre-existing IPs that normally have standard interfaces, like in the case of NVDLA, an AXI interface and an APB interface. I see there's a question, maybe, let me see. Ah, no, okay, just a notification, but not a question. Okay, so before even showing you where NVDLA is and how it's integrated, I'll show you how easy it is after you integrate a third-party accelerator to compile both its software and its, in case the hardware of the accelerator needs to be generated, that as well. So make NVDLA. Again, very fast because I pre-executed the commands to speed up the time, but what this is doing is generating the hardware of NVDLA and then compiling the device driver and also the runtime application. In addition, once that's the compilation is done, it's going to place some files into the root file system of Linux. You see now there is a folder called NVDLA, and inside here there are some files that we just compiled with the make NVDLA command. You have the runtime application. This is a script for testing. There's also a library for the runtime application. And in addition, inside the drivers, there will be the NVDLA device driver. Okay, so automatically this goes inside the root file system of Linux, and if you launch make Linux again, you get a fresh new image of Linux, which has the new updated root file system with the NVDLA files. Okay, now that's how easy it is to prepare the NVDLA accelerator. We will see how you can then integrate it in an SoC. I will just very quickly, maybe let me do it in this other window, show you where we do and how we do this integration. So in the accelerators folder, third-party flow, right now available in Esp. We're working on a few more accelerator integration. We have integrated a few more, but this is the one we released. Basically, what you do for your accelerator is create a simple wrapper, and this wrapper is a Verilog wrapper. It's instantiating the accelerator that you want, and as you can see, it's not doing anything. This is a module provided by NVDLA, so it's like instantiating the accelerator. And this wrapper is just about basically changing the name of the interface signals and doing some mappings, some assignments, so that then you can map the accelerator to the interface that Esp is expecting. In addition to that, you create a simple XML that defines a few things about the accelerator so that the flow becomes flexible. What's the name of the clock signals, what's the name of the reset signals, and a couple of other information like address width or name of the interrupt signal, and so on. We have a full tutorial on this on the Esp website, but I'm just giving you a quick preview. And then there is a couple of other things like the list of the Verilog files to be compiled, and if you have VHDL files as well, and so on. And finally, you need to create a simple makefile which gets automatically called by Esp. And in this file, you create your targets for compiling the software and the hardware of this third-party accelerator. Now, I don't have time to go in all the details. As I said, we have a full tutorial. But the idea is that with 4 or 5 simple steps, and of course, by placing here in this folder the hardware and the software of your third-party accelerator, you can do the integration. Okay, so if I go back to the guide with the steps, we compiled an integrated NVDLA. I explained really briefly how the integration is done, but you can find out more. Now we can finally design some SoCs with the processors available in Esp and with the accelerators that we either generated or were reusing from the Esp release, or we integrated as a third-party accelerator. So this is a step you can do. And we're going to configure 2 SoCs. So I'm going to go actually where I can open a GUI. And we are in the usual SoCs folder. And you can just launch the Esp SoC GUI with this command, make Espx config. This is how the GUI looks. As you can see in the instructions, this is the configuration that we want to do for this tutorial. So I'm going to go ahead. So the processor core is Ariane, and in this case, we're okay with it. And in this case, we're not going to instantiate a cache hierarchy in the SoC. So the only caches in the system will be the level 1 caches of the Ariane core. We are going to do a 4x3 system. And then we select the tiles. Let me try to mimic exactly what I have in the. Whenever you see in this box, whenever you're doing some configuration that is not allowed, for example, here we have 2 CPUs, but we didn't select the cache hierarchy. The GUI will tell you, you need a cache hierarchy to do multi-core. So I believe it was FFT here, FFT here. This is the accelerator. You see how automatically the GUI can find the accelerators that we have generated, all 3 of them. And we can place a couple of NVIDIA array. You can place the tiles wherever you want, and you can place how many of each tile as you want. Of course, as long as they fit in your target FPGA, or if you're going for an ASIC flow, as long as it's not too big for your ASIC area target. Now, one more thing to notice is for the sub accelerator that you created, you had 2 configurations generated, one with DMA 64-bit and one with DMA of 32-bit. Here you can only see the 64-bit DMA because you have the Ariane core. If you choose one of the 32-bit cores, you will instead be able to use the DMA 32 because it matches the network on chip bit width. For the FFT, we didn't really go through the details of that step, but not only you have DMA 32 and 64, but in designing the accelerator, we specified two other options, which is whether the accelerator is working on fixed point numbers of 32 bits or 64. So in this case, we select the 32-bit one for the purpose of the tutorial. But what this wants to show you is that you can, with high-level synthesis and with designing accelerator, you can have a lot of different implementations of your accelerator. You get to generate them automatically, and then you get to select the one that you like and you want to have. And this can also be useful for design space exploration and various types of experiments. Generate the SoC and close and click OK. Now, what you get out of this is this SoC gen folder. And inside it, I guess the most important part is the Esp folder. You have a hidden file called Esp Config. This contains the configuration that we designed with the GUI. You can see here all the tiles and their details. And then for RISC-V, you also get a device tree already automatically generated for you. You can see the CPU, reserved memory, and then you can see how all the accelerators here are present in the device tree as devices, FFT, sub, MV, NVDLA, and so on. This is all automatically generated by the GUI. One additional step after this that is about generating automatically the SoC is something that gets done under the hood normally, but you can also invoke it explicitly. And it's the make socket gen command. With the make socket gen, you generate another folder called socket gen with some RTL code. And this is the part of the architecture, of the whole architecture. These are the pieces that need to get generated based on the configuration that you choose in the graphical interface. And therefore, for example, you can see how there is a wrapper for the sub accelerator automatically generated so that the accelerator can be integrated in the Esp SoC. Okay, before, basically, the things I'm going to show you after require some CAD tools. I will show you full system Rtl simulation and then some FPGA prototyping. Since for those, it's going to be more of me showing a demo to you, let's actually go ahead and configure also the second SoC for this tutorial. And then I will do the demonstration part with Rtl simulation and FPGA prototyping. So we're going to do a second SoC. We're going to move into a different SoC folder. It's a similar FPGA, but it's the VCU128. Because this FPGA board also has Ultra Scale Plus FPGA, just like the VCU 118. We can basically reuse the accelerators generated earlier for the VCU 118 board, just because they share the same FPGA. Otherwise, you would have to, if it's a new FPGA, new technology, you just need to launch again your high-level synthesis command. So we do another configuration. In this case, we change the processor and we choose the Leon 3. It's another open source processor with the Spark ISA. We do select the caches. We have two implementations of the caches. One is in System Verilog, one is in System C, so requires high-level synthesis. So if you go for the System C version of the caches, which is useful, especially when you are experimenting, you're doing architecture research, so there's a faster turnaround. If you choose to do that, you need to make the caches with HLS in the terminal. I will show you in a second. Anyway, we choose the System Verilog ones. We do a 3x3 SoC, and in this case, we do something different, which is instead of having just one CPU, we do a multi-core. And the memory in that example was here, but you can place it wherever you want. And I chose, again, 3 FFT accelerators in this case, because I want to show a nice application afterwards. Generate and close. As I was saying, if you need the caches, you just need to do make level 2 HLS and make last level cache HLS. That's for the System C caches, so that they get generated. Okay, so now we have the configurations. As I showed earlier, you will have the configuration here. You can see we selected a Leon 3, and then you have the accelerators. Okay, now we're gonna do I'm gonna show some quick experiments on FPGA. Before that, I will show you how you can do Rtl simulation of the full SoC that we configured. However, if we simulate an SoC as big as these ones, it will take several minutes. So for the purpose of doing this quicker, I will actually roll back to a 2x2, and we select our new accelerator and everything else the same. Okay. Now, how do you do simulation with the Dsp full system? You do make sim. This one is using model sim. We support other tools. NC sim is for incisive, XM sim is for Cilium. And you're welcome to add support for more tools. Of course, it takes time, but it would be good to have support for more. When you do make sim, all the RTL, including the one that was generated, gets compiled. When you launch it the first time, it takes some time because it's compiling a lot of Xilinx libraries. In this case, I pre-generated some stuff. And you see the compilation is done and it's launching model sim. Now we're in the model sim GUI, and we just you run the application. Now, I just did make sim, which means I didn't really tell the simulation which bare metal application to run on the processor. So it's using the default one that we have here, which says hello from ESP. And that's what we expect to see. First stage bootloader, then hello from EXP. If you want to run a specific bare metal application, you need to define the variable make program. And then you go and point to the bare metal app that we compiled earlier, the XE one. Now this is doing all the same as before, but it's running the automatically generated bare metal test application that you generated with Paolo earlier. I'm going to leave this run. It's much faster than the full big system, but it will take a little bit. and we can go back to it later. But also, anyway, we're going to run exactly the same bare metal application on FPGA, which is going to be much faster. So that's how you do full system RTL simulation. Normally, that's the first thing you want to check with some simple tests, and then you can go on FPGA and run more complex applications. Now, what are the steps for going on FPGA? You need to generate the FPGA bitstream, program the FPGA with the bitstream, and then copy over your bare metal software or Linux to be able to run the software on the ESP system. So also in this case, I pre-generated the FPGA bitstream because it takes an hour or more. And I did something that I also want to say because it's useful. You see how now there are 3 VCU 118 folders. Basically, when you want to have multiple different designs for the same FPGA, all you need to do is you just copy this folder, give it another name, and that's it. So you have multiple working folders. I'm gonna move in the folder with the first bitstream. Paolo, how am I doing on time? Do I have another, I think I need 10 minutes. 10, 15,
I think we're good considering that we started about 20-25 minutes later because of the issues with Zoom, so that people were not able to log.
Okay, I think I should be able to wrap up in 10-15 at least.
Yeah, that's good.
Okay, so we move in a folder where I prepare the bitstream already. How do you generate the bitstream? The command is make vivado syn. If you do make vivado GUI, you don't automatically generate the bitstream, but you create the same project for vivado and you open the GUI. And that's sometimes useful when we do debugging, so that we want to add the debug course before generating the bitstream and so on. But if you just want the bitstream, make vivado syn. And I already ran this, and the result is that you will have a link here pointing to the bitstream. Now, the next step is programming the FPGA. To program the FPGA, we do make FPGA program. Although, before doing this, there are a couple of environment variables that you have to set, because you need to tell the ESP makefile where the FPGA is. So I'll show you the local makefile here, and I'll show you the variables that I'm talking about. So these 2 variables define where the FPGA is connected to program it. So this is the case where the FPGA is attached to the same machine where you're launching your script, but you can also have it remotely attached to some other machine, and these are the fields that you need to change. This is my case, and I already exported these variables in my environment pointing to the server where I have the FPGA at. There are a couple of other variables. The ESP link ones are, again, needed to connect through to the FPGA, but in this case, this is not to speak to the FPGA itself, but it's to speak to the ESP SoC on the FPGA. Basically, through the ESP link tool, you can communicate with the debug unit in the ESP SoC, and you can reset the processor, and you can move the programs into the memory of the system, and so on. Paolo, maybe you want to say a word about how the Ethernet connection of ESP link works, and maybe also the UART and SSH.
Yeah, so basically we've created
really high level.
Yeah, we've created a system in which you can really share your FPGAs across a team, and the FPGAs can be connected to a server, and you can have everybody connect and use ESP on those FPGAs, where basically you can export the UART interface to a specific TCP port. You can export SSH connection to Linux booting on top of ESP to another TCP port. And similarly, you can export the ESP link debug unit to another port. Now, all you see here is default in case you have your FPGA locally attached to your computer and connected to the same subnetwork. So if you connect your FPGA to your router and your computer is connected to the same router, you don't need to change any of this, because even the ESP link and SSH IPs will be taken from automatically generated configuration files in ESP. The only time you need to change this, and this is the case, for example, for Davide, is when, for example, your computer is on one network and your FPGA is under a different subnet. Then you need to have some sort of router with port forwarding, and in that case, you use the IP of the router and the port forwarding that that router is connecting, is using to forward your message to the ESP link or to the SSH port of the Linux running on ESP. So let's just say that as long as you have your FPGA on your desk, you don't have to worry too much about this. There are more instructions on the website. So if you follow the tutorial, it will explain this in details. But the system is built in such a way that you can share this with multiple people remotely.
Exactly. Thanks, Paolo. So I already preset those variables for my specific case. This is something outside of ESP. It's like your FPGA setup. Those variables are just there to help. So make FPGA program. It's programming the FPGA. And then in the meantime, I will also connect to the FPGA. There are two ways to do it. You can use the make UART command of ESP, but in this case, I actually log in into the machine connected to the FPGA. You can see the FPGA is connected. We have this link is connected to this USB. And I'm just gonna connect to the UART to get the terminal outputs with Minicom. You can use other tools too. Minicom is the one we normally use in our lab. So the FPGA is almost programmed. Okay, now we're gonna start by running on the FPGA some bare metal programs, the one we compiled earlier. And by the way, by now, exactly, the bare metal program in simulation that we launched earlier is completed, and you can see this is automatically generated. You generated it with Paolo. What it's doing is it finds out that there is one sub accelerator in the system, and then it's testing it. And in this case, we don't have caches. So normally the default with Ariane is that we have an accelerator only doing non-coherent DMA. So no cache access, direct access to main memory. So now we're doing the same test, but remember that in the big system that we have an FPGA, we put two of the accelerators. So that would be the main difference. Oh, and just like before, when you do make FPGA program, make FPGA run. This is like when we did make sim, it's gonna do the default. It's gonna run the default program. So we should see, hello from ESP, from the FPGA. If we want to run a specific application, just like before, soft build, Ariane, bare metal, substratus, exe. And this is gonna test the sub accelerators. Let's go through the prints. Differently from the simulation, now we have two accelerators, so they get found by the test application, and then they both get tested. And they work with non-coherent DMA. Very, very similarly, we can see the FFT accelerator tested with the bare metal program. And in this case, there are too many prints to see all of them because the font is big, but now you see 3 of them get found and they all 3 get tested. This transfer that you see here is the pre-compiled bare metal program going from my host machine to the ESP system on the FPGA through an Ethernet link. And in addition, after transferring the program, there is a reset of the processor cores so that they can start operating. Now, this was for bare metal. We're gonna do now a boot with Linux on the same SoC. Just to remind everybody, now we're working with this one. this is the system that we put on FPGA when we run make FPGA program. Take 1 second. Okay, and then differently from running bare metal, we need to add Linux to the make target. This is gonna transfer Linux first, so it takes longer because it's around, I think, probably 10-20 megabytes in this case, while the bare metal app was very small. And then we should see the Linux boot here. I think it's taking longer than it should. So let me launch it again.
Davide, it won't work this way because you have reset the
yeah. Let me program and then launch again. Yeah, I have several layers of indirection, so the bar is not loading because I disable it because I have many layers of indirection, but don't worry, I'm gonna just launch it again. It's gonna be fine.
Yeah, you should, when you run it on your machine, you should see the bar progressing. Now, in this case, David is remote, so he disabled that because the shell was lagging a little bit, but you would see the progression bar showing your progress as it loads.
I have 3-4 layers of SSH. Now the board is okay. Let's see, this should be fine. It will take 10 seconds. What we're gonna see then is we're gonna first run the test applications for the accelerators, and then also the ones we generated, and then also for NVDLA. I don't know why. Okay, this time it worked. So we're gonna see Linux is booting on the Ariane core on the ESP SoC. These steps always takes a few seconds because it's the one unpacking the root file system. Say starting the network. The Linux on the ESP system has an IP, so it's accessible through Ethernet. Now, what I want to bring your attention on is what the initialization scripts that ESP has. What they do is they register all the device drivers in the system, and it actually finds out all 3 FFT devices. Then the 2 NVDLA devices are getting registers, and then the 2 sub-accelerators are also getting registers. The list you see here is the full list of drivers that ESP tries to load, but only for those for which there's an actual device, these ones, you will see the registering. With the root open ESP, you can log in the system. What I was saying, the devices are registered, so if you go here, you see that under devices, you have the 3 FFT Stratus devices, or for example, the 2 sub-Stratus devices. Okay. The test applications, they all go under application test automatically. We can test the FFT. In this case, it's only the default application only tests the instance 0. You can easily modify it to test a different instance or test all of them together. So you see it's only testing the instance 0. And the one for Stratus, also the instance 0 for Stratus. And this is for the ESP accelerator, let's call them. For the third-party accelerators, there is a folder generated in root, in this case for NVDLA. And here we have the NVDLA runtime. The NVDLA runtime requires a loadable, which contains all the information about the neural network to be executed. In this case, an input image, and then we say we're going to run on the instance 0. And then let's run in parallel also something on the second instance of the of the NVDLA accelerator. Instance 0, instance 1. You can compile the NVDLA software to not have so many prints, because in the end now all of the times is spent printing and very little computing on the accelerator. But this just shows what's actually happening. And we have the two NVDLAs working in parallel, executing all the 10 layers of the neural network. Okay, the last thing I wanted to show is, I said you have Ethernet access, you can do SSH into this system. So maybe I can show you that I can do SCP to my own machine. And let's see, maybe we can take the Esp logo. So we can SCP from here, insert the password, and you see we are transferring through Ethernet with the SCP. You can do it also from outside using the IP. Well, now it's too up, but basically when you boot, you can find the IP of the ESP system, and you can do SSH and all of that. Now I'm going to repeat all these steps, but much faster for the other SoC, and then I can close this live tutorial session. Also for this one, I prepared the bitstream, and it's the ISPASS 2. Bitstream generated, as we said, all the software is already compiled. Everything is the same. All the steps are the same. While the FPGA programs, I'm going to show you one interesting application that I'm going to run on this new bitstream. See the bitstream, we have 3 FFTs, and so this is a good setup to show you a couple of the features that you can have in ESP. One is the point-to-point communication between accelerators. We're going to invoke all 3 accelerators in parallel and sending data to each other directly. The first loads from memory, sends the output to the second, which sends it to the third, everything through the interconnect and without going to memory. The second is that in this case, I selected, I put a local cache in each accelerator. And so very easily with DSP, you can tell the accelerator in which coherence mode to work. And the accelerator can bypass the caches, can be fully coherent, can be coherent only with the last level cache. We have a few cases. The application that I'm going to run to show that, I want to show the application just to see how the ESP API is being used. We have an initial allocation of data with the ESP alloc. This is data that can be then accessed by both accelerators and CPU, and the CPU can access it as a regular array. And then we have some ESP run calls that run different tests. The first tests with just one accelerator with different coherence. And then the last tests are running a little bit more complex configuration, I will show you in a second, with 3 accelerators in parallel. The configurations, the way they look is something like this. See, the configuration parallel has 3 threads in parallel. Each of them is invoking a different accelerator, and each of them will configure this accelerator in a different way. In this case, they're actually all three using the same, but you see here, it's a different configuration. The configurations look something like this. These are the accelerator-specific parameters. And here, there's a cache coherence type that you want the accelerator to use. In this case, it's non-coherent. But in other cases, here we're using, sorry, here it's a different type. And then here are the point-to-point details. This means there's no point-to-point happening, but slightly different configurations are going to activate point-to-point communication. Okay, so the FPGA has been programmed. I'm going to run Linux. Hopefully this time it will go through the first attempt. Maybe I just needed to wait more last time. And in this case, when we boot Linux, we will also see that it's a quad-core system. So 4 cores are being brought up. This is the Leon 3 core. You can see here, 4 cores. This FPGA design is at 80 megahertz. Some of our open source components cannot really go too much up in frequency. And so it was saying 320 more or less million. Here, 310 BOGO MIPS, because it's 4 cores. All the accelerators registers, as before. In this case, we have 3 FFT. In addition, we also have the caches of the accelerators, the level 2 private caches and the last level cache, which also have a very small device driver that we use for flashing them when needed. So that gets registered as well. Login, root, open ESP. As you can see, if you launch top, you have all 4 cores actively running the OS. And then the tests I wanted to launch, well, we can still launch the FFT test like we did before, only on one instance. But the interesting one, the one for which I showed the code, is the multi-FFT. I launch it. The first test is doing 1 accelerator, non-coherent DMA access. And you can see it's then validating the data. This is the execution time. Same test, but LLC coherent DMA access. There's a presentation a bit later about what all these coherence types mean. There's one with full coherence, which means the accelerator is using its own local cache. 1 accelerator. Then we have a concurrent execution of 3 different accelerators with 3 different cache coherence modes. And so you see the partial execution times at the total. And finally, the test with 3 accelerators, you see linked with arrows, working in point-to-point and exchanging data. So I thought this was a nice test to show you how you can combine multiple accelerators and easily invoke them from Linux with the Esp API. I think that's it from my part. I can take questions. And in the meantime, we can get prepared for the next segment. We were thinking to actually taking a break at this point, but we started late, so I think we are just gonna push through, right? Paolo, Luca.
Yeah, I think so. Yeah.
Should we give 2 minutes to
I think
people?
it's fine, yeah, because
2 minutes to breathe.
yeah, I'm okay with we can resume at 5:10 and then do the last few parts.
You mean
the
11?
hands-on part.
Sure. Depends on.
Yeah,
11:10, yes.
yeah, 11:10. I'll get ready, set up the next presentation. You will also see that we provide some pre-built material so that you can try the experiments without having to go through all the steps of the tutorial. Mainly in this tutorial we will have a first part where we use HLS4ML to generate an accelerator. HLS4ML generates accelerators in C++.
In the
meantime,
Paolo, Giuseppe, can you confirm you
Yeah, we
you
could.
hear the...
We're hearing your audio. No, but we have a problem with the.
Okay, yeah. Okay, yeah. You, I didn't realize it was already playing.
Yeah, Davide, I think you can let me go.
Yeah, let's go.
11:10 now.
So one thing for the sake of time that I did not do earlier was to always go back to our slide presentation, but I think this is a good time to just recap everything all together. We have these 5 segments. Paolo did segment 1 for the System C accelerator. Then I showed you the third-party accelerator flow with NVDLA and the SoC flow to design the full SoC and go on FPGA. Next, we're going to see 2 video tutorials for a flow for designing accelerators starting from Keras, PyTorch, Onyx. These are deep learning accelerators that leverage an open source tool called HLS4ML. And then Giuseppe will show us a video tutorial about the flow for designing accelerators, ESP accelerators with Catapult HLS. So I'm not going to play all of this video, but only up to a certain point, because then the SoC design part is always the same for all the flows. So we have already covered it.
Hello everyone. In this tutorial, I will show one of the ESP accelerator design and integration flows. This flow leverages a tool called HLS4ML that is able to automatically generate an accelerator.
Davide, we have a problem of audio.
Davide, we can't hear anymore. I think you changed something in the audio configuration. We can't hear the audio anymore. Remember when you share? Yeah, we cannot hear you anymore. We cannot hear the video.
Of the tutorial.
Okay, now it works.
Flows. This flow leverages a tool called HLS4ML that is able to automatically generate an accelerator starting from a Keras, PyTorch, or Onyx model. With this flow, then ESP automatically integrates these HLS4ML accelerators into a full SoC, and we will go all the way down to deploy the SoC on FPGA and test it. There's a written version of this guide as well on our website, as usual. Make sure you read there what are the prerequisite tutorials and go over them before getting started with this one. You will also see that we provide some pre-built material so that you can try the experiments without having to go through all the steps of the tutorial. Mainly in this tutorial we will have a first part where we use HLS4ML to generate an accelerator. HLS4ML generates accelerators in C++ for the tool Xilinx Vivado HLS. And then in the second step we will move into ESP, and with an interactive script we will import this accelerator generated by HLS4ML and we will automatically integrate it and test it into ESP. As a first step, we clone the ESP4ML repository. For the purpose of this tutorial, we will be using a Keras model already provided in this repository. So we can move in. You need to install the tool. I've already done it, so I'm not going to run it, but this is the command. Then we move into the example models. We're not going to build a new model ourselves. We're just going to generate one here. You can see from Keras config that the default model is a 3-layer. This is a 3-layer multi-layer perceptron. It's just 3 fully connected layers. In our case, we do want an input and an output. These are not provided, so we provide them on the written guide on the website. You can go on our website, you can go and download them there. We provide very short inputs and outputs. It's only with 8 inputs and 8 outputs. And what you're gonna do is you're gonna fetch them wherever you download them from. It's just these 2 files, and you copy them into this Keras folder. Basically, we took some input and outputs from a branch of this HLS4ML repository, and we just made them very little, very short. So now we're ready to convert the Keras model into a Vivado HLS accelerator. It's pretty fast. Now you see that you have a Vivado HLS project folder called My HLS Test. We're just gonna go inside and run. We're gonna run C simulation of this accelerator. Only the C simulation. Running the C simulation generates this C sim result log, which we're going to use because these are the results produced by the accelerator, already quantized with the fixed point precision of this accelerator, and we're going to use them to validate into ESP. Then this is it. So remember this path, because ESP will need to import this path. I'm already going to copy it for later. Okay, now we can move into ESP. Here I already cloned it. You should go through the prerequisite guides, especially the setup guide. I have to add something here. So this video is recorded with a slightly older version of ESP, so you may see that some of the paths or name of the scripts are slightly different, but on the website the instructions are updated, and in the end everything is pretty much the same, just like some file names and positions in the repository. Everything ready, the toolchain, the environment. Now to integrate an HPLS4ML accelerator, we're going to launch our interactive script for generating accelerators. In this case, we're going to call the accelerator MLP 3 layers. Then we're going to choose the HLS4ML design flow. We're already in the ESP home, which is what I suggest. So for this, we keep the default. Here we can paste the path of the Vivado HLS project that we generated with HLS4ML. Here, this is a 3-digit hexadecimal. It's an ID for your accelerator. Here you can really insert any number that doesn't overlap with other existing accelerators. In the written guide, for example, we say 194. The only limitation is that in decimal, this number should not be bigger than 1024. Okay, the data bit width of this accelerator can be found going into this parameters file. So this is the data type of the accelerator. So it's 16 bits in total and 6 bits of integer part. So we could do 16 bits, but for the purpose of this tutorial we do 32, so we're actually wasting some bits in this case. But as long as this number is bigger than the precision of the accelerator, it will work. And you can choose between 8, 16, 32 and 64. As we saw a second ago, the fractional bits were 16 minus 6, so 10. Then we go back to this file and we can see that the first layer has 16 inputs and the last layer has 5 outputs. So input data size 16, output data size 5. And going back one more time, as I was saying, those input and output files that we moved around, they got transformed into these TB input features and TB output predictions. Each of them have the same number of rows, and as you can see, it's 8 rows. So we have 8 inputs for the test bench. Now this is done. This is all you need to do. Your accelerator is fully integrated in Esp, and from this moment on, all the steps are the same as for what we showed in other guides for System C accelerators or for C, C++ accelerators. So as usual, you move into a design folder. For example, in this case, we choose the VCU 118. I have here a little script to set the environment variables. You make sure you set them as described in the setup tutorial, in the setup guide. And now the first thing we do is we run the high-level synthesis for the Vivado HLS accelerator that we just imported. So this Vivado HLS project. The Vivado HLS project is now, by the way, into accelerators, HLS4ML. You see there is a folder MLP3 layers, which has been generated by our steps. Here, all of these things are generated by Esp. So test bench, the scripts for HLS and simulation, source files, and this is an XML with some information needed by the system. Here are some header files, and instead this HLS4ML folder is nothing but exactly the content of the original MyHLS project. So if you look at this content, you see build project firmware. If we go back to our project here, you can see it's the same. So this is just a copy and paste of the project inside of Esp, plus the addition of all these things for wrapping and interfacing the accelerator with the rest of the Esp system. So how do you run HLS with Esp? You just type the name of the accelerator, it will autocomplete, and then HLS. You can see first that it ran the C simulation with those input files and output predictions that we moved around earlier, and the test passed. So you see how this script not only imported the accelerator, but also added a test bench that works automatically. Now this takes a while, and for all of these steps that take a while, I will just fast forward. Now, what does the HLS step generate? First of all, the whole project is running in accelerators, HLS4ML, name of your accelerator, and there will be an HLS work and then this is the technology, Virtex UltraScale Plus in this case, of your FPGA. So that's the Vivado project. Then once Vivado is done, generated the RTL is placed in tech. Again, the technology of the FPGA you chose, and then in Accelerator, MLP 3 layers. Here you have 2 versions of the accelerator. Inside there you find RTL. Example, here you see the generated RTL. There are 2 versions because we always generate DMA with 32 bits and 64 bits, because the 32 bits will be instantiated when you use the Leon 3 processor, and the 64 bits when you use the Ariane processor. Now we'll see in a second. So now the accelerator exists, it's been generated, and it's in Verilog. We are going to configure an SoC with the ESPx config command. As I said, here when you choose Ariane or Leon, it will change your option for the accelerator. So here, of course, now we can find our new accelerator. You see it's DMA64. If I choose Leon, it goes to DMA32. Okay, so I think this was the main part, and then you recognize the GUI. From this point on, then all the steps are similar to the other flows, because the accelerator flows are different, but then the SoC flow is unified for all different IPs. So I think we can stop there. This was a very good example of one of the hands-on tutorials that you can find on our website and on our YouTube channel. So we thought we would play this one with a video. I think next is Giuseppe talking about the Catapult HLS flow. I don't know if you want to bring up the slide.
I'm sharing the screen. Don't worry.
Okay.
So I think you can see the first slide, and I will play the recording in a second. In this section, we are looking at how to integrate an accelerator that we will design with the Mentor Siemens Catapult HLS with C++ as specification language in Esp. Let me know if you can hear the audio. In the tutorial, I will illustrate how to design an accelerator with the C++ flow
Yes, it's good.
HLS. Please note that Catapult HLS supports both C++ and System C as design specification languages. In the tutorial, I will describe some of the aspects of a C++ synthesis flow. With the ESP team, we are working on the Catapult HLS System C flow and the integration with the Nvidia MatchLib. This tutorial is also available as hands-on material on the ESP webpage. We choose the softmax function as a running example for the tutorial. In machine learning, softmax is a widely used activation function. You find it usually at the end of a deep neural network because it turns scores, floating point values, on an arbitrary range into probabilities. The sum of the output values is 1. The softmax function outputs a vector that represents the probability distribution of a list of potential outcomes. For example, if you're running a neural network to classify animals, softmax returns the probability for the image to be a dog or a cat. You can also see the mathematical definition of softmax. For each value, we have the exponent of that value divided by the sum of exponent of all of the other values. We choose to leverage an open source implementation of the softmax, as it is provided by Mentor on hlslibs.org. This implementation uses piecewise linear approximation and algorithmic C data types, Mentor ACFix. The input and output arguments of the function are parameterized so that the arithmetic can be performed at the desired fixed point precision. This allows the HLS designer to trade off among area and performance. During this tutorial, we will not explore the capabilities of HLS tool for the design space exploration, but we will focus on the accelerator interface, general structure, and integration in Esp. As a preliminary example, this is how you would use the softmax function from Mentor in a generic design. I just want to highlight how the function takes as input arrays, output arrays, use Espx as data types, and that you can choose the precision of the input and output values. For example, here we are using Espx on words of 16-bit, 8 bits for the integer part. The first one has sign, the second one is without sign. We use truncation, and in case of overflow, we choose to saturate. You can find the material of this section on the Esp webpage. The material contains the following code: the HLS project, that is the C++ source code, the test bench and the Mentor Catapult HLS script for the softmax accelerator, and the software, that is the application and the device driver for the softmax accelerator. Apart from minor code edits and console commands, you are not required to explicitly code, but we invite you to review the provided code and scripts when you will try it after the tutorial. To begin with, let's make sure to be in the Esp root directory. We want to move in the accelerators and then Catapult HLS directory. Here we will download the package with the material for the tutorial. We uncompress the package and we remove the zip file. In the next slide we will see the directory structure and some more details about that. We adopt some naming convention for accelerator that we design with Catapult HLS. We use CXX_catapult suffix for the accelerator for the HLS C++ flow. We will use the _sysc_catapult suffix for the System C accelerator. The name of the accelerator for this tutorial in particular is softmax_CXX_catapult. If you have correctly uncompressed the tutorial material, the files for the HLS project and the software application will be in the directories hardware and software. Let's see more in detail the directory structure. In particular for the softmax CXX catapult, we will have an hardware and software directory. In the hardware directory, we have an XML file that contains the accelerator description and the register list, as well as we have an HLS directory for the HLS scripts, some directory for the sources of both the synthesizable code and the test bench. As well, we have a software directory for the bare metal application and for the Linux application that comes with device drivers. Before giving more details about accelerators in Esp and Catapult HLS, I want to introduce a classification for accelerator for heterogeneous system on chip. We can classify accelerator according to how they couple with the processor and the memory. There are essentially two main classes of accelerators: tightly coupled accelerators and loosely coupled accelerators. Tightly coupled accelerators sit in the CPU proximity. They usually share CPU resources, such as the register file and the memory management unit, and the caches. There is no overhead for the invocation, and they are virtually transparent to the software. On the other hand, they require an expansion of the ISA to include special instructions to manage their operation. This ISA expansion percolates to the software via a compiler or via low-level libraries. These kind of accelerators, tightly coupled accelerators, pose time enclosure challenges The logic must meet the same constraints of a CPU and may have limited portability across different designs of different CPUs. The second class of accelerator is the loosely coupled accelerator. They have a greater area budget. They cannot degrade the CPU performance. For loosely coupled accelerator, we are able to tailor the local memories, and in particular, we can move data among the accelerator, the private caches, the last level caches, and the main memory. The Esp accelerators follow this second model. These accelerators are integrated in an ESP instance as devices that we control via Linux device drivers. The ESP accelerators operate on large dataset and they alternate computation phases with data transfer phases. Now let's consider first the interface of an ESP accelerator. The interface of an ESP accelerator has ports that are common across all of the supported HLS flows, as shown here in the figure. And in particular, there are some minor differences that are HLS tool dependent. We will see the details for Catapult HLS in the next slide. But first of all, let's see which port an accelerator, an ESP accelerator, should have. To communicate with the CPU via memory map register, we have a conf info port. These encapsulate essentially the accelerator configuration, memory map registers. Then to program the DMA controller, we have two ports, DMA read control and DMA write control. These encapsulate the DMA configuration. To transfer data from and to the main memory, we have DMA read channel and DMA write channel. Finally, there is a port to notify the task completion back to the software application, AC done. And this can be mapped either on a register or to an interrupt. Given the previous overview of the interface of an ESP accelerator, we can see here the C++ code for the module interface when we run Catapult HLS. You can see that we are using Mentor, AC channels, and AC sync. The AC channels is a communication channel that allows the accelerator to transfer data to and from a top module. When combined with the HLS directive CSS IOPort.css in wait, it ensures that the data is properly synchronized at the interface via latency-insensitive protocol. Catapult adds the proper shaking signals to the Rtl netlist in form of read, veli, and data signal. While the AC sync port is a synchronization channel that Catapult offers for specifying standalone handshaking signals when a designer needs to control the synchronization directly. Essentially, there is no data transfer. And it is here combined with the directive IOPort sync out valid. In addition to the communication and synchronization channels, the accelerator interface relies on the following data types. We have a data type, more properly a C++ structure, for the configuration register that are memory map, conf info t. In this case, for the softmax, there is only a single register for the size of the batch. Then we have a data type to specify the DMA configuration. And in this case, this struct has an index, that is the memory offset, as a field that is length, it is the length of a DMA transaction, and there is also a field size, that is the encoding of the DMA width. This second struct, this second configuration is common to all of the accelerator, while the first one, the conf info, has to be customized according to the necessity of a designer. Finally, the designer can specify the size of the DMA word with the DMA width macro. This can be 8, 16, 32, etc., and that will impact the overall system. After HLS, this is how the interface looks like in Rtl Verilog. You can recognize most of the ports that we have previously defined in C++. Besides the data channels that comes with the suffix _dat, you can notice the additional _ready and _veli channels that implement the latency-insensitive protocols. Let's see hands-on the accelerator interface in C++, how to run HLS, and the same interface in the generated Verilog RTL. We have previously downloaded and uncompressed the tutorial material in the directory catapult_HLS, and at this path softmax cxx catapult hardware source basic softmax.cpp, you can find one of the two implementations that we will present in this tutorial. If we open the file, we can immediately recognize the interface that we have previously defined, where we have AC channel and AC sync primitives. For the AC channel, we have the configuration channel to access memory map registers. We have the DMA read and DMA write controls channels. These are to program the DMA, and then we have the channels to move data from and to the main memory. If we want to run HLS, we have to move to a different directory. In the specific case is SoCs, and we choose a specific target board. Once there, we run the synthesis command. Keep in mind that this makefile get the targets for this makefile get automatically generated when you uncompress the package. Running HLS for this accelerator may take few minutes. Once synthesis completes, we can check the generated RTL code. The RTL files will be placed in a directory that is technology and accelerator specific. Here we can find our Verilog file. It's relatively big. And closer to the bottom, we may recognize the RTL interface for the softmax accelerator, where beside the clock reset, we can find all of the other channels that we have designed in C++, together with the extensions that suffixes that specify that a specific channel is for data or is for synchronization with a latency insensitive protocol, because we have these valid and ready signals. Internal structure of the Esp accelerator. Let's remember that the accelerators in Esp are loosely coupled, and that the accelerator execution consists of 4 phases. There is a configuration phase, and after that the accelerator iterates and possibly pipelines load, compute, and store phases. For Catapult HLS, we have defined 2 different coding styles. A first, more simple, style is the single block architecture, where the phases run in a sequential way and are implemented in a single C++ function. Then we have defined a hierarchical block architecture coding style, and in this case the phases run concurrently one to the other. In particular, to add concurrency, we combine HLS directives with a recommended coding style, while still leaving everything in C++ untime and single-threaded. The synchronization between the blocks will be added automatically during the synthesis process, and we will see these 2 coding styles in a couple of slides. Finally, let me also stress the importance of private local memories in Esp accelerators. In the PLM, the accelerator keeps a copy of the data or a portion of the data from the main memory. The PLM becomes central for the design optimization process because they can be tailored to the needs of the designer. We have usually local memories to support each of the load, compute, and store phases. Sometimes PLMs have to be implemented as circular buffers. In some other cases, they are ping-pong buffers. In most of the cases, the designer has to create PLMs with many ports to sustain the throughput of the accelerated logic. More in general, a properly tailored PLM reduces the latency and increases the throughput of the system. Let's consider the simplest style. The main characteristic of a single block architecture are the phases run in a sequential way and are implemented in a single C++ function, and the private local memories are defined locally to the C++ function. You can see here the pseudocode for the softmax function, and we will see the C++ implementation in a minute. This is just to give you an overview of the implementation in a single slide. On the top, we have the interface that we have previously defined, here, the signature of the function. And later on in the function, we define the local memories, the PLMs, as arrays. Then we have the configuration phase, where we read from the conf info port the memory map register. In this specific case, we read the batch size of a softmax. That is the number of times we later on iterate over load, compute, and store. During the load phase, we configure the DMA controller with the offset in main memory and the amount of data we want to load. We use the DMA read control port for this. Once the DMA is programmed, we can start reading the DMA read channel and saving data in the PLM. For the compute phase, we leverage the mentor softmax, and once the computation is completed, there is a store phase. Similar to the load, we configure the DMA controller, and then we start storing data back in the main memory. The actual code for the single block architecture is pretty similar to the pseudocode. The only implementative detail that I want to highlight is that it is necessary to explicitly enforce the serialization between the DMA configuration and data transfer subphases of both the load and store phases when coding them in C++ for Hpls. For example, you can observe here again the single block architecture, the simplest one, and later on in the code we may observe the configuration of the DMA read channel. How this configuration is performed. We define a flag, DMA read control done, and we iterate over this DMA read control done by using a non-blocking primitive. We try to write DMA read control until we succeed. When we succeed, we have a true value for this DMA read control done. Now later on, we test that variable. Essentially, we force a serialization between the DMA control up here and later on the data transfer. If you do not use this simple trick, the final RTL code is not functionally correct. And what we observe, what happens, is that the data transfer starts before the configuration of the channel has completed. And you will notice that if you run a Rtl simulation, obviously that would cause an error. Here you can see the coding style that we have adopted for the hierarchical block architecture. The main characteristics are that the phases are coded as separate C++ functions. The PLMs are globally defined and shared among the functions. Note that Catapult offers the modeling construct AC channel to allow the users to directly model the data exchanged between blocks of a hierarchy. While in software, function can exchange data via shared arrays of variables, this becomes problematic for Hpls, since the synchronization of data exchanged between blocks must be inserted automatically by the synthesis tool. Because of the inherent complexity associated with this, Catapult offers the modeling construct AC channel to allow the users to directly model the data exchanged between blocks of hierarchy. Note that the user can use the AC channel to model both I/O streaming and memory interfaces. Here at the function interface, we have the I/O streaming. While here, later on, we are declaring the PLM as AC channel, and those memories are passed as parameters to the load, compute, and store functions. In addition to AC channel, in this coding style, we use AC sync for the synchronization of the processes and blocks. The AC sync are passed as well to the various functions, and when all of the processes have completed, they synchronize via the synchronization primitive. Finally, at the end, we return the accelerator done signal. As array sizes become larger, it is typical to map them to memories during HLS because the area and power cost of mapping to register becomes prohibitive. In Catapult, the arrays that are shared between hierarchical blocks get automatically mapped in a ping-pong memory structure. This ping-pong memory structure consists of 2 or more memories that are written and read in such a way that the blocks can run concurrently. And this is useful and is one of the key aspects of the accelerator in Esp, being able to tailor the PLM to keep the maximum throughput of the accelerator. Finally, in addition to the above HLS directive, a coding style must be followed to ensure that extra memories are not inferred by error. First of all, you have to remember to encapsulate the shared array in a struct, and then a local struct with the package array should be declared to perform the memory operation, and this local struct is optimized away if the coding style is carefully followed. For example, in the load function, when we transfer data from the main memory to the shared input PLM, we should declare a temporary version of the PLM, a local instance. We have to iterate over this local instance and read data from the DMA channel, and only finally write the local instance back into the PLM. The same applies for the store phase, where we read the output PLM into a temporary copy and use this copy to transfer back data in memory. In both the cases, the temporary copy will be not present in the generated RTL, and there will be only one shared memory structure between the top module and the sub-modules. We are getting close to the end of the tutorial. The last thing to do is to create an Esp instance with the design accelerators. Once the Esp SoC generator graphical interface is open, the very first thing that I want to do is to make a little more room for my accelerators. I increase the number of columns in the NOC. Okay, from now on I think it's pretty similar to the previous flows. I think the general idea is that we make a little more room on this graphical interface and we can instantiate the various accelerators. I stop here and I take any question. Okay.
I can take over the screen in the meantime for the next presentation.
I think, Davide, you can go ahead now.
This is the last segment, no, Davide?
Yeah, now what I'm showing you is what Giuseppe just presented, and we have a slide to recap all the flows that you've seen. It's just a more detailed drawing of the same picture that we used as a guideline. So we showed you some live tutorials and then some recorded tutorials on how to design new accelerators with different flows and how to integrate third-party accelerators. And we saw how all of these different flows eventually, once you have the accelerator IPs ready and their software ready, all the flows converge into the same SoC design flow. So you build the software, configure the SoC, and you can proceed with evaluating your SoC with full system simulation or FPGA prototyping, and then eventually also with an ASIC flow for taping out a chip. Now to conclude, the last demo session that we have is interesting because it's both an example of an architecture research project that you can do with DSP, but also it shows you some of the features that we have today implemented in ESP. In addition, this demo is also showing a feature of ESP that we didn't talk much about yet. And it's the fact that ESP has several hardware monitors in the SoCs that you can create. And you can easily add more. And on top of that, ESP has a way to access those monitors in real time in two different ways. One from the processor within the same SoC. And the one that you will see in this demo is through, again, an Ethernet link connected to the SoC. And that way, from a host machine, you can access the hardware monitors of the ESP system on the FPGA. So for this demo, we have a 5 minutes video that I'm going to play. Just like before, let me know if the sound is fine. And I'm just going to play.
In this demo, we are demonstrating on FPGA our work on reconfigurable cache coherence models for accelerators. There are three main cache coherence models for accelerators. The non-coherent model has accelerators bypass the cache hierarchy and do direct memory access to the DRAM. The last level cache coherence model, which we introduced, has the accelerators send their memory requests directly to the last level cache without keeping coherent with the private caches. Lastly, the more processor-like model is the fully coherent model, where all the accelerator transactions are kept coherent. The accelerator can either have a private cache or can send requests directly to the last level cache, and these requests are kept coherent with recalls. Our work, as well as other recent literature, shows that no model is the absolute best. The best choice of cache coherence varies at each accelerator invocation, depending, among other things, on the number of active accelerators, their memory footprints, and their memory access patterns. We designed support for all the cache coherence models, such that the coherence models are completely transparent to both the programmer and the accelerator designer. The cache coherence of each accelerator can be dynamically selected at each invocation. To confirm the potential benefit of all of this, we designed an adaptive algorithm that dynamically chooses the proper cache coherence model at each accelerator invocation. The algorithm is once again transparent to the programmer, and it makes introspective decisions based on the current status of the system. Now let's dive into the FPGA demo. First, we are loading a bitstream of our SoC on a Virtex 7 FPGA. This script first deploys the bitstream on FPGA and then loads Linux SMP and starts the boot, which we will follow in this other window through Minicom. In the meantime, we're going to launch on a host machine a monitor GUI, which collects live statistics from our system on chip on FPGA through an Ethernet link. Here we're just showing some of the data graphically, but the monitor data coming out of the SoC is really useful to perform architectural exploration directly on FPGA. By taking a look at the monitor GUI, while the multi-core boot completes on FPGA, we see that on the top left there's the SoC under test, which counts 2 memory controllers, 2 CPUs, and 12 accelerators. These are distinct synthetic accelerators with a wide range of communication properties. At the bottom right, we have a graphical view of the NOC traffic, but only for the 2 bidirectional DMA planes. The router-to-router links will be colored to indicate the amount of traffic.
Just to clarify, what you see here, just like the demos before, is an ESP system on FPGA with several accelerators, and the GUI that you see with the monitors is running on a host machine connected to the FPGA through Ethernet.
Once logged into Linux, we launch a synthetic application and then launch the data collection in the monitor GUI. If you look at the terminal on the left, you'll see the LLC argument, which means that in this case, all accelerators are running in last level cache coherent mode. The second argument, none, means that we are letting Linux choose freely where to allocate memory. The application currently running is composed of 9 phases, where the first phases have at most 1 active accelerator at each time, whereas the last phases have up to 12 active accelerators. Phases also differ in the size of the workloads. As the execution proceeds, you can observe the NOC traffic in the GUI. And then once the execution will end, we will take a look at the final statistics of NOC traffic. By looking at average and max, we can see that more traffic went to the memory controller at the top left and that many NOC links have not been used at all. Now we will re-execute the application by enabling our adaptive algorithm. Notice the auto argument in the terminal. And with the second auto argument, we are also enabling some policies for better distributing the memory allocations across the 2 memory controllers. These policies do not affect performance significantly in this case, but we will see clearly a much better distribution of the traffic. As a first result, in the terminal, we can see that the per phase execution time is decreasing. And we can also notice how many more NOC channels are used and that the traffic is spread out more evenly across the SoC. We can now look at the average and maximum NOC traffic, and we see how it's really spread evenly across the SoC. Here are the results after running the application with 2 other baselines, all accelerators non-coherent and all accelerators fully coherent. Our adaptive algorithm, represented by the first bar, reduces both execution time and off-chip accesses. To conclude, this experiment was able to successfully exploit the cache coherence reconfiguration capabilities of our architecture, and all of this is transparent from the point of view of the programmer. Thank you very much for your attention.
Okay, so this was an next example of using Esp for architecture research, and you also saw the monitor GUI, which is really nice, I think. I hand over to Luca, who's going to talk about Esp for teaching and then some concluding remarks. I'll stop sharing, and if there are any questions, of course, feel free to ask.
Okay, can you hear me? Yeah. Let's also start video. Thank you, Davide. So just a few words in conclusion about other opportunities that the Esp offers, particularly with respect to teaching system-on-chip architecture and programming in the classroom. So one course that we have developed at Columbia University, leveraging a lot of our experience in developing Esp, is a system-on-chip platform for 868. Is an upper level curriculum course taken by undergraduate and master student and PhD students. Is a foundation course on the programming, design, and validation of system on chip, with emphasis on high performance and better application. We have been offering for almost 10 years now, and the goals are really mastering the hardware and software aspect of integrating heterogeneous components into a complete system, designing new components that are reusable across different systems, product generation, implementation platform, and evaluating design in a multi-objective optimization space. This course is described in quite a bit of detail in a paper we published a couple of years ago, which is available on the Esp website and is cited at the bottom of this slide. At the end of this course, students are able to work on the design of a project of an accelerator using high-level synthesis and high-level programming languages like the one that we have illustrated during the tutorial today. So what you see in this slide is the live activity recorded of the design project done in the 2015 edition of the course, where students were distributed in across about 21 teams, and they were competing in designing an hardware accelerator for the wide area motion imagery gradient kernel during a month period. You see the dates on the top right corner changing while the chart gets populated with more and more dots. Each dot corresponds to the implementation of one accelerator evaluated in the bioobjective optimization space, where area is here estimated through equivalent lookup tables on an FPGA, and performance is estimated as an effective latency. That means clock cycle necessary to execute this particular task, the gradient algorithm, multiplied by the clock period. So of course, as your points are closer to the origin, the better they are with respect to either one or both of these objective metrics. And you can see the triangle dots that represent the Pareto optimal points. And this shows various things. Shows that students at the end of the class can really develop optimized version of this accelerator. And each of these implementations is different in terms of microarchitecture, in terms of performance and areas trade-offs. But each of them can be integrated within an ESP system using the system of socket interfaces and services that we are presented today. Over the years, we kept improving not just the course, but also the project. So introducing new elements, so elements of collaboration and design reuse across the teams. So for instance, we started in 2016 by having half of the class designing a discrete cosine transform accelerator and the other half designing an inverse discrete cosine transform accelerators. And so here you see the live recording of the performance of each team over the last month. And then also we created, leveraging the same concept that you have seen today, there is the ability for each team to reuse one of the component designed by another team and combine it with the component designed by the team in order to obtain a complete system that uses both the DCT and the IDCT. And more recently, we have further developed this by having the parallel design by different teams of students of different layers of a neural network using, again, some of the flows that you have seen today with respect to particular domain-specific accelerators that ESP accommodates. And again, here, one could notice that each of these components is designed by a different team and can be combined with the components designed by the other teams in a very seamless way, thanks again to the interfaces and the socket that we explained today. So this is for this first class. And then we have also developed another course called Embedded Scalable Platform 6868, which is a natural follow-up, which has the previous course as the prerequisite. And in this course, actually, after having learned the basics and the foundation of system-on-chip design, accelerator design, students work on more individual projects, designing accelerators and integrating them into larger system for a particular algorithm that they find interesting. And so for this course, we have actually inserted in the ESP website under the resources tab, a new web page that you see here in a snapshot, which gives us some of the guidelines to organize this type of projects based on ESP. And so this is something that we will continue to improve and upgrade, and we are welcoming feedback, and we hope they can inspire teachers at other university to use our infrastructure. So this brings us to the end of this tutorial. We thank you for your attendance and your interest in ESP. In conclusion, we contribute to ESP to the open source hardware community in order to support the realization of more scalable architecture for system-on-chip that integrate more heterogeneous components, thanks to a more flexible design methodology, which accommodates different specification languages and design flows. So you have seen, hopefully, the flexibility and the modularity of both the ESP architecture and the ESP design methodology. ESP was conceived as an heterogeneous integration platform from the start and tested through years of teaching at Columbia University. So now we invite you to use ESP for your projects and actually to contribute to ESP and perhaps to sign up to some of our channels where we, like the YouTube channel or the Twitter channel, where we inform the community about the latest advances in ESP. So unless there are particular questions, at this point here, there are just some references and a thank you from the whole ESP team.